Up to now, we've delved into examining Edwards' short descent and refining it with a little tweak. We introduced a first Fermatean-like descent to show Fermat's little theorem, and then explore squaring through Pythagoras triples, both as a standalone method and then as an additional tool to complement the other methods we discussed. Next up, in this section, we're diving into a completely fresh infinite descent method. It's going to lay the groundwork for the method we'll tackle in the following section, which just might be Fermat's unpublished infinite descent. Fermat's little theorem provides n squared plus 1 equals p times k as a first equation from where to start a descent. So it's trivial to see that the square of u times n plus u squared equals p times k times u squared is also true for any integer u. And so the square of p minus u times n plus u squared must also be divisible by p. As with the binomial expansion, the prime number divides all terms including the square of u times n plus u squared. So, as u grows, p minus u times n will decrease until it reaches its minimum at around p over n ratio, and then will start to rise again. Let's see a couple of examples. The first example is the case prime 281. Fermat's little theorem provides the initial equation, and with that we construct the second one, derived a few moments ago. So we can see how trying growing numbers for u sub I, the values for the other square, that is 281 minus 53 times u sub I, and of k sub I, will first decrease, find its minimum, and then increase again in absolute values. In fact, the minimum value of 281 minus 53 times u sub I is reached when u sub I is the integer next to the 281 over 53 ratio, which is 5. You can see that in the table and in the graphic. So you find the desired solution. 16 squared plus 5 squared equals 281. The example is the case prime 2777. Fermat's little theorem provides the initial equation, and we see that the second equation evaluated for u sub I at 15, which is the closest integer to the ratio 2777 over 190, let us find the smallest value of k, that is k equals 2. So we now know that 15 squared plus 73 squared is the double of 2777. Given that both squares are odd, we can add and subtract these values and divide it by 2, arriving at the solution. 29 squared plus 44 squared equals 2777. When k is bigger than 2, we have choices available. We can solve it using Edwards' short descent and or squaring through Pythagorean triples. But here's the cool part. When we combine those two values Fermat's little theorem gives us for the starting equation, a beautiful formula emerges. In fact, Fermat's little theorem provides the initial sum of two squares, n sub 1 squared plus 1, where n sub 1 is bigger than 0 and smaller than p. Then, we also have a complementary sum of two squares, n sub 2 squared plus 1, where n sub 2 equals the absolute value of p minus n sub 1. And so the square of v times n sub 2 plus v squared equals p times k sub 2 times v squared for any integer v. The next step is proving that the square of u times n sub 1 minus v times n sub 2 plus the square of u plus v is also divisible by p. Expanding the terms and regrouping shows that the first and second terms are clearly divisible by p. So we have to prove that it divides the third term too, so as to know if p divides the sum of two squares at the left of the equal sign. Replacing n sub 2 as p minus n sub 1 and regrouping, we see that p divides both terms. Thus, p divides n sub 1 times n sub 2 minus 1. And so p divides all three terms at the right side of the equal sign. And so p also divides the sum of the terms at the left side of the equal sign. The beautiful formula simply equates p with that sum of two squares. As a side note, see that the sum of squares encompasses all potential combinations of squares divisible by p. For prime 53, then we find through Fermat's little theorem that 30 squared plus 1 equals 53 times 17. And so 23 equals the absolute value of 53 minus 30. So the formula for this case is the square of 30 times u minus 23 times v plus the square of u plus v equals 53 times k. Below there are the values for each square for all combinations of u and v bigger than 0 and smaller than 8. You can check the table showing the same color for a specific value for the second square. So we are on the hunt for the right u and v values to make this equation work. Given that n sub 1 and n sub 2 are co-primes, otherwise they would have a common factor with p, Bezout's lemma assures us that suitable values of u and v can be found, which can be determined using Euclid's algorithm. But as we actually don't know the decomposition of p as x squared and y squared, in order to find u and v, we require value checks. This time considering that v sub I equals the integer value rounding up n sub 1 times u sub I divided by n sub 2 to reach the smallest solution. This beautiful formula provides the solution in remarkably few steps compared to merely checking values for x in p minus x squared equals y squared. Moreover, it can be further optimized. During value checks, if you chance upon a quotient of p whose decomposition into a sum of two squares is already known, you can employ Edwards' short descent or squaring through Pythagorean triples to potentially reduce the steps even more. Well, let's see the case prime 3541. Fermat's little theorem provides the initial equation, so we get 2689 for n sub 1 and 852 for n sub 2, and we insert them in the beautiful formula. We'll eventually find out that we get the solutions for u being 6 and v being 19. But there's also another pair of u and v that reaches the same solution, which is 13 and 41 respectively. In order to get those values, this time instead of a single u curve, we now have a family of curves, one for each u sub I. But each curve will have its smallest value at the absolute value of 2689 times u sub I over 852. Just replacing that value in v sub I, you minimize 2689 times u minus 852 times v. As you see in the column, you do reach that couple of pairs of values. That's nicely graphed below, highlighting the couple of pairs. In the second graphic, the x-axis changes, representing u plus v, showing the smallest values for each u curve. Needless to say, every minimum value is a sum of two squares, so you could try Edwards' short descent or other methods to reach the final solution. So this would involve checking some values, and as p increases, those numbers to be checked increase too. But we can limit those values. As we aim to represent 3541 as x squared plus y squared, the beautiful formula implies that either x is u plus v or y is u plus v. So we can safely assume that x is the biggest of both squares. Then, the range that has an upper limit of the square root of 3541, which is close to 59, as 60 squared is 3600, bigger than 3541. And the lower limit of the range is when x and y are almost the same. That is the scenario when 2 times x squared would be equal to 3,541. So the lower limit is the square root of half the value of 3,541, which is 42. This limits the cases to test to only 4 pairs, 11 and 35, 12 and 38, 13 and 41, and 14 and 48. But this can be narrowed too, as u and v cannot have a common factor other than 1. Otherwise, that common factor would divide k, and so k would be bigger than 1. And as the greatest common factor is 2 in the second and fourth cases, that narrows the cases to evaluate to only 2. So we see that the first case doesn't provide the solution as k equals 17, but the third case does provide the solution desired. Nevertheless, in this particular case, the solution is also obtained from the 2 discarded cases once common factors are factored out. As a conclusion, the beautiful formula offers a concise set of potential solutions that require numerical verification. Considering the size of P and the n sub 1 over n sub 2 ratio, the length of this list would be close to 1 minus 1 over square root of 2 times n sub 2 over n sub 1 times the square root of P, where n sub 1 is bigger than n sub 2. Add to that u and v may have 2 as a common factor. So for the case u must be even, but v may also be even every 2 cases, 4 cases, etc., depending on the n sub 1 over n sub 2 ratio. So the length of this list will reduce to the range half to 3/4 of that previous value. When n sub 1 is much bigger than n sub 2, then the list of cases reduces drastically. For example, for prime 351,289, we got that n sub 2 is 5,064. Then the formula is close to 2, and so we need to verify just 2 cases for u and v, 7 and 479 and 8 and 547. And when n sub 1 is very much the same to n sub 2, then the solution can be found fast, just trying the first natural numbers. As n sub 1 times u minus n sub 2 times the absolute value of n sub 1 times u over n sub 2 tends to 0. Again, the beautiful formula coupled with a short list can yield a complete solution when combined with previously introduced tools like Edwards' short descent, the little tweak, and squaring through Pythagorean triples. Next, we'll explore how to adapt the beautiful formula to construct a fully deductive infinite descent.